Hey everybody, this is a 201 final project, digital audio filter light show. This is Mohammed Gandhi.
I'm Spencer Perry.
I'm Eric Weissman.
I'm Justin Roberts.
Okay, so we have for subsystem 2, we're using the analog in as AI, and for the pinout we have PT B0. As always, do not exceed 3.3 volts. For our analog out, we have it set as A out, and we're setting the pinout to be PT E30. So also we set float AI2. That's going to initialize our float, which is going to be like a fraction for our while loop later on. And we initialize our A out 3, A out 2, A out 3, A out 2, A out 3, and A out 4. And then we go ahead have an amplitude. We basically just multiply it by 3 and initialize it as an integer.
Alright, so now inside the while loop we have our AOut2 variable, which we are going to set to be a floating average equation. And what that does is every time, the first time it runs through, AI2, AI3, and AI4 will be empty. And from there on out, the variables or the values of the variable will shift down to the right. So that'll be constantly constantly updating the signal we're evaluating. Here we have AOut3. We set the input signal from the analog in to be subtracted by the filtered or the floating average that we established. And then our last line right here is just to amplify it so that the optocouplers will receive the signal and turn on the lights. Alright, in this lab we used a FRDM KL25Z microcontroller. Here's the pinout. We needed 3 connections, 2 inputs, one input, 1 output, and 1 to the ground. We have right here, we're establishing a common ground, so we just take this ground output and bring it to the breadboard. This is our audio in signal that we're receiving from the phone. This can't exceed 3.3 volts or it will blow the microcontroller. And then finally we use the analog out pin up there to convert the analog signal, the digital signal back into analog to send it to the optocouplers.
A general overview of this whole subsystem 3. First you start off with your microcontroller, which you already finished your filter. You send it into the optocoupler here, which has an LED built inside. It goes through and it's sent to the other side of the optocoupler, which is now forward biased because the light is now on. So the switch is closed. So you send it from here into your triad. And your triad is here because of your 120 volts and your 3.3 coming out of your microcontroller again. It then goes through your resistor to your load resistor to your light, which is powered by your 120 volts AC, and it flips on and off. The optocoupler is useful in the system because it prevents high voltages from affecting the system that is receiving the signal. Over here we have 120 volts AC, and because we have this optocoupler here, it doesn't affect microcontroller, which only kicks out 3.3 volts. The triac is used for alternating current in either direction. Here we have 3 different pins, seen here. The triac is useful in this system because of the gate. The gate allows us to take signal from the optocoupler and bring it into our system that has 120 volts. And then you're allowed to have current in either direction, A2 or A1, as seen here.
In conclusion, we were able to build a low-pass digital filter by using the free-scale microcontroller and a C code. If we had more time, we will add a high-pass digital filter and using digital output instead of analog output to have high-pass and low-pass go into the subsystem 3, and we will use another light bulb to distinguish the high pass and low pass filter. That receive the signal coming from the iPhone, and we will able to distinguish the voltage output of the iPhone as maximum, which is 2.7, go into the audio input, sending to the subsystem 2, which is the free scale. We use C code to build a digital filter that will be going to subsystem 3, which is contains the optic couplers and the triac to separate the 3.3 volt and the 120 AC in the circuit, going to the light bulb.
Space Head.